Hello friends, welcome to lecture number 11 of this chapter. So in the last lecture we have done concentration terms part 1. This is going to be the second part of it where we're doing the remaining concentration terms. So in the last lecture we have done weight by volume, volume by volume, molarity, molality. And today we'll be doing the remaining ones. So without any further delay, let's get started with the next concentration terms. So the next concentration term that we have to study now is, it was I think the 1, 2, 3, 4, 5th, 6th one, mole fraction. Let's study mole fraction. Mole fraction is denoted by the Greek letter chi. You can call it as chi. Chi, not chi, of course, chi. Okay. So let me define it for you first of all. Suppose there is a container which has two gases, gas A and gas B, two substances. Suppose this is one Na moles and this is Nb moles. Then what is the mole fraction? So mole fraction of A, which is chi A, will be nothing but moles of A by total moles. That's the definition. Moles of one component divided by the total moles. So chi A is equals to nothing but Na divided by Na plus Nb. Whereas chi B will be nothing but Nb divided by Na plus Nb. So that's how we can define it. That's how the definition goes. Now, this kind of mixture is called as binary. It's called as binary solution. Therefore, for binary solution, what will happen if I add chi A and chi B? If you add it, you'll get it as Na divided by Na plus Nb and plus Nb divided by Na plus Nb. So when we add them up, it will give me Na plus Nb on top, Na plus Nb at the bottom. So see what will happen? Yes, it will become 1. So chi A plus chi B will become equal to 1. This becomes the formula which we may have to remember for binary solutions only. If it is not binary solution, then it will be say chi A plus chi B plus chi C, whatever will be equal to 1. It always remains true. If we add all the mole fraction, it will come as 1. That's the rule. This is how we can find mole fraction. Let's do a question on this. So one question. See, we're done with. You can take a screenshot. Let's go to one question. So suppose there's a container which contains 2 moles of neon, 1 mole of hydrogen, and 3 moles of argon. So the question is, find the mole fraction of neon, mole fraction of hydrogen, and mole fraction of argon. How to go for this question? So let us solve it now. So let's solve it. So the solution, first thing first, let's find the formula. Formula for the mole fraction of neon will be number of moles of neon divided by number of moles of neon plus number of moles of hydrogen plus number of moles of argon. Right? So what is the number of moles of neon? Neon is 2 moles. See, in the question it's given 2 moles divided by 2 plus 1 plus 3. So what will be the value? It will be 2 by 6, which is 1/3. See, 1/3. What is the mole fraction of hydrogen? That will be moles of hydrogen divided by moles of neon plus moles of hydrogen plus moles of, yes, argon. It will come out to be 1 divided by 2 plus 1 plus 3, which is 1 by 6. So can you guess the third one? Of course, it will be 1 by 6 as well. 1 by 2. Yeah, of course. So mole fraction of argon will come out to be number of moles of argon divided by number of moles of neon plus hydrogen plus argon. Right? So the total comes out to be 1 divided by 2 plus 1 plus 3. The top is 3, yeah. So 3 divided by 6, which is half. Right? It will be half. So based on this, we got 3 things. Moles of neon is 1/3. Moles of hydrogen is 1/6. And moles of argon is half. This is how we can find the mole fractions of each of the components. Okay, now let's go to the next concentration terms. The next concentration term is parts per million, ppm. Parts per million. Okay, so let's do this. See the simple definition. What is per million? Before that, let me ask you, what is percent? Percent means what? Per means every, cent means 100. That means out of every 100, what marks we are getting. Similarly, what is part per million? So ppm is nothing but mass of solute divided by mass of solution into 10 to the power 6. This becomes the ppm, right? That's how we can define ppm. Let's do one simple question. If 2 milligrams of A is dissolved in 10 grams of B, what is the concentration? Find the ppm. So how to go for this question? Very easy. The question can be solved in a very simple way. ppm will be nothing but mass of A by mass of solution, right? So let me take it as 8, so that the things can be made simpler in calculation. So let's assume that this is 8. Okay. So what is the mass of solution? We'll add them up into 100. So what's the mass of A? So mass of A is 2 milligrams, meaning 2 into 10 to the minus 3 grams. What's the mass of B? 2 milligrams, 2 milligrams plus 8 grams. Now this adding this makes no sense. We can just take it as, see, we cannot add them, right? Like 8 plus 0.0002. Adding this makes no sense. It's almost 8, right? So 8 into 10 to the power 6. So gram cancel. What do you get? We'll get it as 1 by 4 into 10 to the power 3, meaning 1000 by 4, 250 ppm. See, that's it, 250 parts per million. So this is how we can approach questions of ppm. So we have discussed two concentration terms as of now. One is mole fraction, the other is ppm. Now we have last one left, which is formality, and then we have another topic called as normality, but I'm not going to do that. And now we'll be doing that in the chapter redox reaction, which is going to be just next chapter after this. So as I finished doing the numericals of this chapter, I'll start with redox reaction, and that's where I'll tell you normality in detail, because that is actually a topic of redox reaction where we'll actually get the essence of why we study that. So don't worry, that video is coming up soon on normality. For now, let's study formality and let's finish off this concentration term. What's formality? I know it sounds very funny, but yeah, formality is nothing but F, nothing but number of moles of ions divided by volume of solution in liters. See, it is same as molarity, but the only difference is it is only for defined for any compounds. That's it. Molarity is defined for anything, but this is defined only for ionic compounds. That's the only difference it has. And nothing else. Simple. Okay. So one last thing before I wind this video. See, there will be question asked in your exam, so you must know this particular concept. See, let's understand. Chi M. See, chi mole fraction, molality. See, chi M molality, mole fraction, molality. What else? We have weight by weight percentage. See, weight by percentage. So all these terms, ppm, another term, they all are written with small letters, right? See, since they're written with small letters, they're all, I'm just giving a shortcut, they're all temperature independent. They don't depend on temperature independent. Why? Because they all are small letters. That's how you should remember. Formality, molarity, density, see, weight by volume, all these, these parameters are capital letters, right? So they are temperature dependent. So this will help you to remember the stuff, you know. So another one I have included, night normality also. So these are the terms which are temperature independent. So these two are very important topic that you must remember. So that's it with the concentration terms. And we have done all the theory required for concentration terms in part 1 and part 2. In the next part, that is the next upcoming video, will be all about numericals of this chapter. We'll be doing previous year paper questions and all those. So stay tuned to my channel for the upcoming video on questions. So I hope this concept of concentration term is clear. See you soon in next video. If you like the video, please subscribe to my channel, share it to your friends, like the video. Thank you.